Yeah, what's up?
It's the one to ask you about. I think I remember-ish what it was. I just wanna know for sure how to approach it.
Okay.
So it was something about, sorry, I ran up the stairs.
Do you want me to open up the test?
Oh, you can.
Okay, here we go. So for the reaction given below, what quantity of heat will be produced if 2.04 moles of C3H8 are consumed in the reaction? Okay, so where do we start?
2.4.
What you're given, right? 2.04 moles of C3H8. Good? Okay. Now, do we have a balanced equation?
Yes.
Yeah, it's balanced. So that means for every one of these, we have how many oxygens? 5. For every one propane, we have 3 carbon dioxides. For every one propane, we have 4 waters. For every one propane, we have 488 kilocalories. Good? So that's what we're going to do. 1 mole of C3H8, so that the moles will cancel, right, is the same as 488 kilocalories. Moles go away. We're left with kilocalories. It asks what quantity of heat. Well, we're in quantity of heat already, so we just multiply and divide. So 488 multiplied 2.04 is either that one or that one. I don't know for sure without a calculator, but what is it? 995 point something, rounds to 996 kilocalories. There it is. Does that make sense?
Like, it can't be that easy.
It's just dimensional analysis. Once you get it down, yeah, it's really not that difficult to figure out a story problem. I know story problems have been always growing up, right? It's like, I hate those so bad. I don't even know where to start. But if you use dimensional analysis, it makes it so much more simple. Not easy, but simpler,
I
right?
think my problem is I went from 2.04 to like grams and moles, and then I didn't know what to cancel because it didn't make sense.
Yeah.
That completely threw it out.
So when you have heat in there, just treat it like the mole to mole ratio.
Thank you.
Good? Anything else? All right. So we're in chapter 8 now, is that right? Okay. Well, let's see. If you're good at algebra, basic algebra, I'm not talking about college algebra. If you're good at basic algebra, if you're decent at it, then this chapter's not too bad. Okay? So if you're not there, then I'll try to help you get there. Okay? All right. So we're talking about gases today. Let's talk about the kinetic molecular theory, first of all. Okay. A few things I want you to know here. So, and this is all about gases here, this whole chapter. So gases consist of many particles moving at random. consist of many particles moving at random. So if you think about in this room, it's filled with air, which is a gas, right? So how many gas particles are in here? Trillions and trillions and trillions and trillions of them, right? Okay. One breath of air is 1,000,000,000,000 molecules. So there's a lot, yeah? And they're just bouncing off each other, bouncing off the walls, bouncing off us. Everything in here, they're just randomly moving, okay? Does that make sense? Okay. The amount of space occupied by gas particles themselves is much smaller than the amount of space between particles. The amount of space occupied by gas particles, I should say, is much smaller than the space between particles. So here's a particle right here. They don't take that much space up, right? But the space between particles, much, much greater. Makes sense, right? So this takes a little bit of space here, a little bit of space here, but the space between it is much, much greater. Yeah? So there's a lot of empty space in between these gas particles. We good? Okay, the next one. So remember we talked about intermolecular forces? Okay, so the attractive force between molecules. So for gases, there's basically none. There is some, but why is there basically none? They're far apart, right? There's a lot of space between them compared to their actual space they take up. So gas particles do not have, how should I say this? We can say, maybe I should change this, sorry. The attractive forces between gas particles is negligible. Negligible. Is that right? Okay. So there is some, but we just assume basically kind of like the mass of an electron is 0, but it's not, right? But we don't really count it because it's basically 0. So same thing here. Negligible force between them, so we'll just kind of ignore that. Are we good there? Does that make sense so far? Okay. The next one, the average kinetic energy of gas particles is proportional to the temperature. Do you guys remember what kinetic energy is? Energy of motion, good. The average kinetic energy of gas particles. So this is kinetic energy. Or motion, energy in motion. So the average kinetic energy of gas particles are proportional to, I don't like to just say proportional to, I'll just say directly proportional. You guys understand that term? Directly, gosh. Proportional to the temperature. So gas particles are moving, they are moving, right? So what happens when they move faster? They hit it into more things, right? And when things hit, causes what? Friction, and then heat comes, right? So the temperature increases as these particles move faster and faster. Good? Does that kind of make sense? Okay? No? Are we good? Yeah? So a little bit of physics here, right? But okay, don't say that, right? Okay. And then the last one, collisions of gas particles are elastic, meaning what? They'd hit into each other and bounce off without any loss of energy. Now, is there any heat when they hit off to each other? Yeah, just a little bit, but compared to everything else, that's the most elastic collision there is, right? There is a little bit of loss of energy, but basically it's 100%, almost 100% elastic. Okay? Does that make sense? Just bounce off each other. Okay? And why is that? Because they don't even have to touch to bounce off, right? Why? Because they might be, well, they might touch. We'll ignore whether it does or doesn't. Are we good? Okay, so that's the kinetic molecular theory, and there is a question on the exam regarding that. And if you look at the, can I look at yours real quick? And if you look at the exam 4 study guide that I just gave you, it says know how the kinetic molecular theory predicts the pressure and temperature that pressure and temperature are directly related. Okay, so now let's talk about pressure and temperature right now. Okay. So pressure, I'm just going to give you an equation. This might, well, if you don't like the equation, if you want a word definition, I can give it to you. But pressure, basically, the equation is equal to the amount of force divided by the area. Okay, so think about Okay, you have a bed of nails, yeah? Can you guys imagine a bed of nails? All right. You do a handstand on it. Well, you do it because I can't. You do a handstand on your bed of nails, and is that going to hurt?
Yes.
Yeah, that's going to hurt. What if you laid all the way down on a bed of nails?
No.
It might be a little pokey, but it's going to be okay, right? Why? Because we have a big area when we're laying down, and the force, the weight is the same, right? So whether we do handstand, all of our weight's on our hands versus all of our weights spread out through our body. Big area, so if we have a big area right here, we divide by our force by a big number, makes the pressure smaller. Does that make sense? But if we have a little area, or just do a handstand on it, well, we divide our weight by a tiny number, well, it's going to be a lot bigger. Make sense? So that's what pressure is. And so if you remember pumping up your bike, right? As well, maybe you do that these days. But what's pressure measured in?
PSI.
PSI. What does that mean?
Pounds per square inch.
Pounds, that's a force, per square inch, that's an area, right? So if you forget what that is, you can just kind of, oh yeah, PSI, that's what that means, okay? Now, pressure is measured in a few different, so PSI, that's what we use when we pump up our bikes or our car or whatever. But in science, we have to use something different, right? Why? Because I think the people who use something different is here in America, we use different things. There was a little video I saw on the other day, and it was the founders of our country, and they was in their 1800 suits or whatever, and they says, yeah, and we're going to use inches. 12 inches is 1 foot. Why? Because that makes sense, right? It's like, what? But really, we got this from probably England. That's where we came from or whatever. And we just took that, and then they changed, but we didn't. So really, that's what happened, okay? Anyway, but kind of funny. So the one unit of pressure that we use is millimeters of mercury. Why do we use millimeters of mercury? If you look at the old thermostats, they have little tubes and they have mercury in it, right? So the atmospheric pressure is pushing up the mercury, and it kind of reads how much pressure we have. And you can have inches of mercury now, I mean, here in America, but okay, millimeters of mercury. But we kind of got away with that a little bit. And so that's equal to 1 torr. 1 millimeter mercury is equal to 1 torr. And again, what's torr? We don't use that very much. But sometimes we still use millimeters of mercury because it's just ingrained and that's just what we use, okay? But 760 millimeters of mercury is the same as the SI unit of pressure, which is 1 ATM, which was atmospheric pressure, 1 atmosphere, okay? So that is a good conversion factor to know. And I don't know, do you have to memorize this? Let's see. Yeah, it's here. It's on our reference sheet. So, and the cool thing, the equations that we're going to learn this chapter, they are basically on this sheet. There are a few that are not, but I'll show you how to get them from our reference sheet. Okay. So this is basically the one that I need you to know. You don't really have to know that, but if you see torr, it's the same as millimeters of mercury. You might be asked on your homework how to convert torr to atmospheric pressure or millimeters, whatever, okay? We good with pressure and what the units are? So make sure you can convert millimeters mercury to ATM or vice versa. That will be on the test, okay? Okay, volume. Volume we measure, well, a few different units here. Liters we use a lot, but in chemistry we often use milliliters, and in the medical industry we use what? Cubic centimeters, right? cc's. You guys familiar with those, maybe? But if you remember, so cubic centimeters, centimeters cube, or cc's, right? 1 milliliter is the same as 1 centimeter cube, or 1 cc. That's something you should know. And of course, liter is 1,000 milliliters, right? We should know that. And then, of course, temperature is measured in what?
Kelvin.
Kelvin, that's right. So temperature is measured in Kelvin, or capital K. And we need to know this. Well, I think it's 0.15 really. And you are given that on your reference sheet as well, okay? So most of this stuff, these are the only two that you kind of need to just know, okay? Any questions so far? So it's mostly just facts that I'm giving you right now, right? So section 1 on our worksheet is just converting Celsius to Kelvin, Kelvin to Celsius, ATM to millimeters mercury to ATM. You want to practice a couple? Yeah, let's do it. So let's do one of each, and then I'll let you guys do the rest. How's that? And it also has liters to milliliters. We've done that, but we can do it again if you'd like. All right, let's do the first one. We have 23.5 degrees Celsius, and we will got to convert that to Kelvin. So we're just going to plug it in this guy here. So 23.5, and we're going to add 273. So we plug the temperature in Celsius into the Celsius part, right? And that's going to give us our temperature in Kelvin, which is 296.65 Kelvin. And remember, it's not degrees Kelvin, it's just Kelvin. Good? We okay with those? Can you go the other way? Right, we'll just have to subtract 273.15 to both sides, and you got it, right? Then let's go ahead and do the next one. If we have 2.35 ATM, atmospheric pressure, and we got to convert this to millimeters of mercury. So we're going to start with what we know, 2.35 ATM, and we're just going to convert using dimensional analysis, okay? We don't want ATM, so that goes on bottom. We're looking for millimeters of mercury, goes on top. And what's the conversion factor?
There's 760 millimeters of mercury for every 1 ATM.
Yeah, and again, that's on your reference sheet. You don't have to memorize that, right? ATM goes away, and it should give us a 17 86 millimeters of mercury. Okay. We good? Do you guys want to practice some of these on your own right now, or what? Yeah? Let's try it. Doing okay? Ready to move on? All right, so on this study guide, we didn't really talk about, we read number one, but we didn't really respond on it. So, know how the kinetic molecular theory predicts pressure and temperature are directly related. What does directly related mean? One increases, the other increases, right? Or one decreases, the other decreases. So, if we increase the pressure, what's happening? So there's a lot of space in between molecules. What happens if we increase that pressure? They get closer. They're going to hit into each other more often. If they're hitting into each other more often, then what? More heat, right? More friction, more heat. So more temperature, directly related. Higher pressure, higher temperature. Does that make sense? And then number two, we just have to know how to convert ATM to millimeters of mercury or vice versa. Okay? So far we got 2 points on the exam. If we understand those, right? Yeah.
We might talk about this later, but you know when you have a pressurized can of something and towards the end of it, it gets really cold?
Yeah?
So, do they add something to like make it cold to counteract?
Yes, aerosol.
Mm-hmm.
So it's kind of like, it doesn't have to do with the pressure, and that's why it's cold, so it's not cold because of the pressure, but it's probably not as hard as I'm thinking. I'm just not thinking of it. I can look it up and let you know, but yeah, we probably won't get there unless you want. I mean, I can look it up, but anything else?
I wanna ask something.
Okay, go ahead.
I could obviously ask Google, but I don't know. So, because we're speaking of pressure here, and I don't know why I've never understood pressure, because we can't see it, right? Like,
Mm-hmm.
like you can tell me this room's pressurized, I'm like, no, it's not, and then it explodes, I'm like, oh, well, never mind. But,
And then you go up in the mountains and your ears
yeah.
start popping, right?
Yeah,
Okay.
like stuff like that, but I don't know if anyone remembers, there was like, I'm not trying to keep this short, there was a accident that happened with people who go like deep dive and like
Uh-huh.
engineers and stuff. They forgot to depressurize the chamber, and that guy literally got sucked into like outside so fast that his body, sorry guys, gruesome, but he literally just became mush. And I like hearing those stories because it's interesting, but I don't understand how badly it can affect their bodies, and I don't know, like an airplane has to be pressurized so you literally don't die,
Yeah.
but I just don't, I think it's because we can't see it, you can't.
Well,
I don't know.
our bodies are designed, you can call it designed or made or whatever, to withhold a certain pressure. And it's kind of like you buy some fish, right?
Yeah.
Buy some fish, and before you put it in your tank, you have to kind of let it get used to it, right?
Yeah.
It's the same thing with pressure. I mean, our bodies can get used to it if we're there for very long. But if you just go right down deep in the ocean, well, you have this much. So the top of the atmosphere to the earth, that much air on top of us. So that's our pressure, right? If you go up up the mountains, your pressure decreases, right? Because there's not as much. But if you go deep in the ocean, you don't have just that air. You have all that water on top of you, and so your pressure just increases a lot.
It's generally something I've thought about a lot, and I don't know, it's just interesting how much it can affect us, it can kill you, just.
Yeah.
Like scuba divers, they have to slowly come
Uh-huh.
up. I mean, I know the reason of that's a biological reason, but pressure, but thank you, that makes sense.
Yeah.
The fish.
We good?
Yeah.
Any other non-chemistry question? No. No, this is good. Because if you can't use what we're learning, then why learn it, right? So, good. Okay, let's see. The next part, when we talk about the individual gas laws, so we're going to talk about the individual gas laws. I can derive these for you or just give them to you. Who wants them derived? And if you actually, maybe I should have derived them because then it helps to understand a little bit more. Okay, I answered my own question. Thank you. All right, we call the next one Boyle's Law, and I don't care if you know who come up with these laws, right? So here they are. And at constant temperature, in fact, maybe I should put constant temperature up here. Oops. Up here. So this could be any temperature, but it's staying the same, okay? And so we can use this, we can use Boyle's law when temperature remains constant. So we know that pressure is proportional to 1 over the volume, okay? Do we know that? Let's see. If we make the volume bigger, what happens to the pressure? Gets smaller, right? Because, well, if we take a big tank, or a small tank of oxygen gas, right? And we make the volume bigger, so we open it up and fill this room. is that pressure going to be different? Yeah, it's going to be way less pressure in a big volume. But if you think about this, just like we did with pressure and force and area, right? If we divide by a big number, it makes it smaller because it's inversely related. Do you see that relationship, guys, or proportionality? Okay. So that kind of makes sense that this is true. All right, so if we want to make this a formula or equation, then pressure is equal to some constant multiply 1 over volume. Okay? So whatever constant that is, who knows, then now we have an equation. Okay? So let's multiply both sides by volume. That way we can solve for the constant. So we have our constant K is equal to, and this is a lowercase k or whatever, is equal to volume times pressure. Or maybe more familiar is pressure times volume, but doesn't matter, right? Same thing. Good? And if that's a constant, that means it doesn't change. You with me? So we can say pressure 1 times volume 1 is equal to pressure 2 times volume 2 is equal to pressure 3 times volume 3, and so on, right? So that gives us this equation right here. Does that make sense?
Do you mean it's either P or V equals to P squared, or is it P and V?
P multiplied by V, because we multiplied both sides by volume, right? And so that's equal to our constant, so it's going to stay the same. So if we change our pressure, what's going to change? Our volume's going to change to continue to be constant, to be the same number. You with me? And so this is a formula that we can use. This is called Boyle's law. But we can only use that if temperature is constant. So it turns out that this is the temperature, but we won't worry about it for a minute. Okay? Are we good there? Okay, so let's do an example. So let's say our original pressure is equal to 65 millimeters of mercury, and our original volume is 600 milliliters. Okay, so now let's say at the same temperature, the pressure is increased to 385 millimeters of mercury. Now let's just think about this. If the pressure increases, what happens to the volume? Increases, decreases, those are the options. So if the pressure increases, so we go from 65 to 385, it gets more pressure, right? The same temperature, what happens to the volume? Well, here's the cool thing. If we know this equation, we don't have to get a headache because we're thinking too hard, right? Let's solve for it and see. But if you understand it, then you can, when you get your answer, you say, oh yeah, it should be that, right? Okay. So pressure 1 times volume 1 equals pressure 2 times volume 2. And again, this is at constant temperature. And you have to know that it's constant temperature, otherwise you can't use this equation. You with me? So now we're looking for volume 2, right? So we divide both sides by pressure 2. So if we increase pressure, we divide by a bigger number. It's a little easier to see it now that we have the equation there, right? We divide by a big number, it's going to make what? The volume smaller, right? But again, we still don't have to know that. We still don't have to see that. 65 millimeters of mercury times V1, which is 600 milliliters, divided by P2, which is 385 millimeters of mercury. What cancels? Millimeters of mercury cancel. We're left with milliliters. Good. So that's what we're looking for, volume. So 65 times 600, divide 385, and it should give us 101 milliliters. We can see the volume goes down. Because our original thing says pressure and volume are inversely related. Good. So one goes up, the other goes down. Good? So can you see yourself doing a problem like this? If you have the formula, right? And if you look at this, the formula is not on there. But when we're done with all of this, I will show you how to get it from here. Yeah? Or you can put it on your little 3x5 card and we're good, right? Your call. Okay? But you need to know this. There will be an exam question on that. Good? Okay. So let's go to another law. So that's our first gas law. Any questions so far? The next one is Gay-Lussac law. And this one is at constant volume. And so we just talked about this. And pressure is, how is it related to temperature? Directly or inversely? Directly. If we increase the pressure, we're going to increase the temperature. If we increase the temperature, we increase the pressure, right? So they are directly related. And if we want to change this to an equation, we could do the same thing. Pressure is equal to some constant times temperature. You with me? Now let's solve for this constant so we can figure out what it is. Divide temperature to both sides, and we got our constant is equal to pressure divided by temperature. And since it's a constant, can you guys come up with Gay-Lussac law? Pressure 1 over temperature 1 is always constant. That means it's equal to pressure 2 over temperature 2 is equal to pressure 3 over temperature 3, and so on, right? Are we good? So again, you don't have to be able to come up with this. I'm just showing you kind of what we know and kind of what equation we can come up with. And again, since the volume is our constant, well, that's our constant volume right there. Now let's do a problem with this one. And here, since we have temperature in this one, temperature must be measured how? In Kelvin. Must be. Do you understand why? No. Because what if we have a negative degree Celsius? That's going to throw everything off. What does that mean? Right? But if we have Kelvin, it's always a positive number, always. And negative temperature, if you think about it, doesn't make any sense. No sense whatever. Yeah, we make sense of it in our mind because we're used to it. But well, we don't make sense of it. We're used to it, right? Okay? So it must be measured in Kelvin. So always convert that degrees Celsius to Kelvin first. Okay? All right, so let's do an example here. Say we have a basketball, somewhat, and the temperature is 10 degrees Celsius, and in the evening it's 10 degrees Celsius, and the pressure is 720 millimeters of mercury. So this is our temperature, okay? The next day after sitting in the sun, so now we go to our new temperature, is 34 degrees Celsius. We want to know what the pressure of the basketball is. So this is going to be our temperature 1, pressure 1, temperature 2, pressure 2. You follow? So the volume of our basketball didn't change. It stayed constant, right? But the temperature changed, so that means the pressure is going to change. What do you think? The temperature went up, so what's the pressure going to do? Go up. Remember, pressure and temperature are directly related, right? But again, we don't have to know that. If we do, we can kind of look at our answer, say, does that make sense? Well, okay, yeah. If it goes up, the other goes up, we can see that, yeah, that's good. But let's use our formula here, which is P1 over T1 equals P2 over T2. And we're looking for P2, so let's multiply both sides by T2 to get P2 all by itself. And then we can just plug our values in. Should we plug in 34? Why not? Has to be in Kelvin. So you got to know that. Put that in big bold letters. You got to have temperature in Kelvin and highlight it, star it, whatever you got to do. Okay? So let's do that first. 10 degrees Celsius plus 273 Kelvin is equal, or 273 is equal to temperature in Kelvin, right? So that means this is 283 Kelvin. Good? And then 34 is going to be 273 plus 34. That's 307. Did I do that right in my head? 34 plus 273. Okay.
307.
307? And I didn't add the 0.15. I probably should. And your answers will probably be based on this formula here. So let's do that. This is going to be, sorry, I'm so used to just saying 273, I forget. So that's 0.15 Kelvin, right? This is 0.15 Kelvin. Good? So now if we plug this in, so we have P2 is equal to this right here. So T2 is 307.15 Kelvin. P1 is 720 millimeters of mercury. And T1 is 283.15 Kelvin. So what cancels?
The Kelvin.
Kelvin cancels. We're left with millimeters mercury. That's good because we're looking for pressure. And we do that, multiply and divide, and we get 781 millimeters of mercury. So we can see we increase our temperature, our pressure increases as well. Good?
Is there
Yeah,
It just happened.
yep, sure is. We increase the temperature, pressure increases. Yes. Good? All right, the next one is Charles' law. Or Charles's law. And Charles's law, so Boyle's law was constant temperature. Gay-Lussac law was constant volume. So Charles' law is constant what?
Pressure.
Constant pressure. Can you guys come up with this formula right now? Okay. You don't have to. I'll give it to you. Okay, so we know that volume is proportional to temperature. If pressure stays the same, temperature increases, it's going to push them out more and more, increase. So think about, you guys, I don't know if you've ever done this, you blow up a balloon, okay, you tie it off, and then you put it above some boiling water. It gets bigger, right? You increase the temperature, the volume increases. You ever see putting some balloons in liquid nitrogen? Pretty cool. Have a tub of liquid nitrogen. You could just put a ton of balloons that are blown up into liquid nitrogen, and you just put a ton of them in there. And then you pull them out, and they go back up, right? They inflate because the gas is in there, but when you decrease that decrease that temperature, the volume decreases as well. Does that kind of make sense? So if you can kind of see that, or actually if you do it at home with the next time you get a balloon, just, okay, I'm going to try this. Put it on, what?
Is that how a hot air balloon works?
Not quite.
Because I don't trust
So,
I'm like,
well, that's because you're way up high, and if you fall out, you're dead. So it's kind of like,
yeah.
I mean, there's a lot of those things that are probably good Russian stuff, like if you're jumping out of an airplane, skydiving, it's like, oh, that'd be so fun, but there's a big risk, right? I'm never going to do it. You can see why, but like, yeah, I could do whatever, but. So anyway, so we can say, okay, let's change this to an equation. Volume is equal to some constant times temperature, right? What are we going to do? Divide temperature to both sides, right? Figure out what that constant is. And our constant is equal to volume divided by temperature. And so what is our formula, ladies and gentlemen?
V1 over T1 equals V2 over V2. No, sorry, T2.
Yeah. Are we good? Because the ratio of volume and temperature, if pressure is constant, will always be the same. Making sense so far? Okay. And we could do a problem similar to the last ones, right? Let's do one. Okay, so we have a hot air balloon. Oh, we're dealing with hot air balloons in this one. But it's not why hot air balloons rise. Why do hot air balloons rise? Because hot air is less dense, right? So it's going to, okay.
Really? I thought there was more to that.
That's it.
That's all? Sorry.
No, you're good.
Like,
So hot air, we say hot air rises, and that's because it's less dense. Okay? Another way to think about it is hot objects always tend to go toward the cold. Heat to cold. Because cold is the absence of heat, so cold doesn't travel, but heat does, right? All right. Let's say, so we have a hot air balloon has a volume of 955 liters at a temperature of 56 degrees Celsius. What's the temperature of the hot air balloon if the volume decreases to 875 liters. So again, we could just call these V1 and T1 and this T2 and V2, right? Because this is our initial case or our first situation, this is our second situation. Does it matter if we say, can I say the ones on my left is my second situation, the ones on my right is my first situation? Yeah, it doesn't matter. It doesn't matter because they're equal, right? So then we take this equation, V1 over T1 equals V2 over T2, and we're solving for what? T2, so can we just cross multiply? Get rid of that ugly fraction. Do you guys understand cross multiply? Understand why we can do that? No? Let me show you. Well, this says divided by T2, so what are we going to do to get rid of it? Multiply by T2. Whatever you do to one side, do the other side. So there's the cross that way, right? And then we can do the same thing over here. But we're solving for T2, so let's just multiply T1 to both sides, right? And we got T2, is this too sloppy? Equals V2 times T1, where is it? Well, I have V1 on this side, right? Almost lost that guy. Are we good? And we're looking for T2, so let's divide it by V1 to both sides. And I got that there. So that T1 comes over here. There's the cross multiply. So it might be a little easier to just, right? But your call. All right, so then we can find T2, but what do we do before we find T2?
You gotta convert to Kelvin.
Change temperature to Kelvin. Yeah, in this case, we only have one. So we have 56 plus 273.15 equals something. 329.15 Kelvin. Okay, so that's going to go in for our, that's our T1. So now if we plug our values in, V2 is 875 liters. T1 is 329.15 Kelvin. And V1 is 955 liters. Am I going too quickly? We following what I'm doing? And what cancels?
The liters.
The liters go away, leaving us with Kelvin, right? All right. So we should get an answer of what? 301.6 Kelvin is our T2. So since our volume was lowered, our temperature was increased. Hold on.
Our temperature was lowered also.
Oh yeah. I was looking at this 56. Hold on, that's not how it should be. Yeah, our temperature is lowered. Mm-hmm. Good. Good? Okay, two more ideas and then we could be done for tonight, or we can keep going. How are we feeling?
I want to be selfish and leave out trick or treaters.
Good idea. Good idea. I'm not going to let my last class do that because they're going to start at 7. Okay. All right. So let's see. So Avogadro's law is the last one. And do you remember Avogadro? The 6.022 times 10 to the 23? And whenever we deal with that number, we deal with what? Moles, right? Yeah. So we're not going to deal with 6.022 times 10 to the 23. Isn't that nice? Okay. So Avogadro's law, it doesn't matter what gas we have. All gases behave the same at a certain temperature and pressure. Okay? So they all behave equally. Whether you have oxygen gas, nitrogen gas, carbon dioxide gas, doesn't matter. They all behave the same. And so if we have a standard temperature and pressure, often just called STP, standard temperature and pressure, then we have a conversion factor. We can go from moles to liters, moles to volume, okay? So how often is it that we're going to have, well, what is our standard temperature? Our standard temperature is 0 degrees Celsius. And our standard pressure is 1 atmosphere. Okay? How often are we going to be in a situation where we have 0 degrees Celsius and 1 ATM? Probably never, right? But this is one that we know. And I'm just going to use this and let's see, do we need to... yeah, there is one problem. Given at STP, we can use this, right? But the thing is, in a higher chemistry class, you'll be asked to figure out that. But first of all, you have to find out what it is, 1 mole per how many liters at a certain temperature and pressure. But we're not going to do that in this class, okay? Sorry. But anyway, so. Here's the I'm just going to tell you. So at standard temperature pressure, 1 mole of any gas, and again, this only works for gas. If we're dealing with a solid or liquid or aqueous solution, it doesn't work. It has to be a gas. 1 mole of gas is equal to 22.4 liters of that gas. But that's at standard temperature and pressure. So know that. For one problem anyway. Good? And so if we're converting grams to moles, moles to moles, and then moles to... So if we say, okay, if we have, let's say, H2 plus O2 gives us H2O, for example, right? And this is a gas, this is a gas, and this is a gas, okay? If we want to say, okay, if we start with actually, let's say if we start with 3 liters of gas, because we usually don't measure gas in grams, right? If we have 3 liters of hydrogen gas, and we want to know, well, how many liters of water will we make? So what's our first step? Balance. Yeah, we're going to do that, but we got a balanced equation, right? Yeah. Man, why'd you always mess it up, right? Sorry, I threw it off, didn't I? Okay. So we got to balance this. We got 2 over here, we got 2 over there. There we go, right? Then, yeah, we start with what we know. And if you want to just sit back and watch me, you can. But this is where it could be applied, right? So 3 liters of H2. Well, where do we go from there? Well, we know if this is at STP, has to be at STP before we can do it, okay? Then we can change 22.4 liters of H2 into 1 mole of H2. You follow? And then, if we want to go to, we're really looking for how many liters of H2O, so we got to go to something else. So how do we go to something else once we're at moles? Mole to mole ratio on our balanced equation, right? So what's the mole to mole ratio here?
So 2 moles of H2 for every 2 moles of
Yeah. So it's 2 to 2. So we have 2 moles of H2, so that they cancel, to 2 moles of H2O. It's not always going to be the same, but okay. And then we want liters, so 1 mole of H2O to 22.4 liters of H2O. That's kind of nice. That's kind of nice. Oh, we have 3 liters of H2O. Done. Good. So this is stoichiometry. I'm just showing you how we can use what we learned last unit using a different conversion step, right? Okay. But again, has to be a gas, and it has to be at STP, standard temperature pressure, 1 degree Celsius and 1 atm. Good? All right. Let's look at the worksheet. And we can do section 2. Do you want, which one of the, I mean, I can do all of these, but then we won't get out of here early. And I don't care if you don't get out of here early, because I can't, right? I'm just teasing. So, do you want to go over one of these? Just to kind of, so the first one, in fact, it's just one of each, using all 4 of these laws that we just learned. Okay, the first one says we have initial pressure and, let's see, and volume. So here it doesn't say constant temperature, but we're only dealing with pressure and volume, so we can assume temperature is constant. So we're going to use Boyle's law, P1 V1 equals P2 V2, right? So if you want to have these on your reference card, that might be a good thing. I will show you a little bit later tonight, or probably next time actually, how we can use a formula on here to derive the other formulas. So I don't know if that's something you'll be interested in, or if you want to just write them on your little reference card. Might be easier that way, right? So do you want to do one of these together, or do you want to just do those on your own? You tell me. Yeah? Which one? First one on the left? Top left? Okay. Okay, it says the initial pressure and volume of a balloon. So pressure 1 is 1